In 1981, astronomers pointed their telescopes at a region of space roughly 700 million light-years from Earth. They expected to find galaxies, hundreds, maybe thousands of them, clustered together the way matter naturally behaves in the universe. Instead, they found almost nothing, and that's when the silence became deafening. This wasn't just empty space. The universe is mostly empty space, but this was different. This was a void so vast, so impossibly hollow, that it violated every model scientists had built about how the cosmos organizes itself. They called it the Boötes Void, and even today, more than 4 decades later, no one can fully explain why it exists. The discovery happened almost by accident. Robert Kirshner and his team at Harvard were conducting a routine survey of galaxy redshifts, standard method for mapping cosmic distances. They were charting familiar territory, expecting predictable patterns. But when they compiled their data from the Boötes constellation region, something was clearly wrong. The measurements kept coming back empty. They checked their instruments. They recalibrated. They waited for new observations. The emptiness remained. What they had found was a spherical region of space, approximately 330 million light-years in diameter. To put that in perspective, if our Milky Way galaxy were the size of a coin, the Boötes Void would span a distance greater than a football field. And in that entire football field, you might find just a handful of coins scattered randomly. The average density of galaxies in this region is roughly 1/10 of what it should be. Some areas contain nothing at all. But here's where the unease begins. Cosmic voids shouldn't be this large, not according to the physics of structure formation, not according to everything we understand about how gravity pulls matter together after the Big Bang. The universe began as a nearly uniform sea of matter and energy. Over billions of years, tiny quantum fluctuations, microscopic variations in density, grew. Under gravity's influence, dense regions pulled in more matter, forming the cosmic web we observe today, vast filaments of galaxies surrounding hollow voids. This process is well understood. It's predictable. Computer simulations reproduce it perfectly, except when it comes to places like Boötes. The simulations show that voids this large shouldn't exist given the age of the universe. There simply hasn't been enough time for matter to evacuate such an enormous volume of space. It's like finding a massive bubble in solid concrete that somehow formed without any explanation for what pushed the material away. Early theories suggested observational error. Perhaps the galaxies were there but somehow obscured or mismeasured. But subsequent surveys with more powerful telescopes confirmed the original finding. The void was real. Then came the uncomfortable questions. What if something pushed the matter out? Standard cosmology offers one explanation. Perhaps this region started slightly less dense than average. After the Big Bang, over 13.8 billion years, matter would naturally migrate away from less dense regions toward denser ones, gradually amplifying the contrast. But the mathematics of this process impose strict limits on void size. The Boötes void exceeds those limits, not by a small margin, by a factor that makes physicists deeply uncomfortable. Some researchers propose dark energy as a culprit. This mysterious force, responsible for accelerating the universe's expansion, might behave differently in certain regions. If dark energy's repulsive effect was slightly stronger in the Boötes region billions of years ago, it could have pushed matter outward more aggressively. But this creates a new problem. Dark energy is supposed to be uniform throughout space. Regional variations would require rewriting fundamental cosmological principles. Then there's the dark matter hypothesis. Dark matter, the invisible substance that outweighs visible matter, 5-to-1, forms the scaffolding, along which galaxies form. What if a massive underdensity of dark matter exists at the void center? This would explain why galaxies never formed there. But again, the numbers don't quite work. Primordial density fluctuations, which we can measure precisely from the cosmic microwave background radiation, weren't extreme enough in that region to justify such a massive dark matter deficit. Here's what makes this genuinely unsettling. The void isn't unique. Astronomers have since discovered other supervoids, the giant void in Canes. Venatici spans 1.3 billion light-years. The KBC void, which may actually contain our own galaxy, extends nearly 2 billion light-years across. Each discovery adds another data point that doesn't quite fit our models. Each one whispers that something about our understanding of cosmic structure, formation is incomplete. In 2015, researchers noticed something else peculiar. The cosmic microwave background, the ancient light from the early universe, shows a cold spot in the direction of a supervoid called the Eridanus supervoid. This shouldn't happen according to standard physics. Photons traveling through vast empty regions should actually appear slightly warmer due to a phenomenon called the integrated Sachs-Wolf effect. This cold spot does the opposite. Some physicists have speculated about exotic explanations, parallel universes colliding with ours, topological defects in spacetime, or unknown fields that interact differently with radiation. Most scientists resist these exotic scenarios. The principle of Occam's razor suggests simpler explanations should be preferred. But as more supervoids are discovered and measured, the simple explanations become increasingly strained. What's particularly unnerving is the possibility that these voids are still growing. As the universe expands and dark energy becomes more dominant, underdense regions may continue evacuating matter at accelerating rates. In the far future, trillions of years from now, these voids could expand to encompass most of the observable universe, leaving isolated galaxy clusters, separated by unimaginable distances of true nothingness. But there's something else researchers discovered that nobody expected. Inside the Boötes Void, in the few places where galaxies do exist, something appears different about them. These rare void galaxies show unusual properties. Some appear younger than they should be, as if their formation was delayed. Others show signs of disturbed morphologies, suggesting traumatic events in their past. Most puzzling, some exhibit higher star formation, rates than comparable galaxies in denser environments. This contradicts expectations. Galaxies need material to form stars, and voids by definition lack material. So why are these isolated systems producing stars so vigorously? One hypothesis suggests that void galaxies, lacking nearby neighbors, experience fewer gravitational disturbances. This peaceful environment might allow them to retain their gas reserves longer, fueling extended periods of star formation. But this doesn't explain the delayed formation times or the morphological disturbances. Another possibility: these galaxies aren't native to the void at all. Perhaps they fell in from the void's edges billions of years ago, carrying with them the scars of whatever violent process expelled them from their original homes. If true, this implies that void formation wasn't a passive evacuation but an active expulsion. Something pushed these galaxies inward while forcing most matter outward. What could generate such forces? In the late 1990s, a controversial idea emerged: bubble nucleation. In some theoretical frameworks extending beyond the standard model of particle physics, false vacuum states can decay catastrophically, creating expanding bubbles of true vacuum. These bubbles expand at nearly the speed of light, transforming the properties of spacetime itself within their boundaries. If such an event occurred in the early universe, it might leave behind a signature: void, a region fundamentally altered. By the phase transition, this remains deeply speculative. No experimental evidence supports vacuum decay events in our universe's history, but the idea persists because it offers an explanation for why supervoids seem to defy standard structure. Formation models. They wouldn't be products of structure, formation at all. They'd be scars from more fundamental physical processes. Most physicists consider this unlikely, but they also can't definitively rule it out. There's another angle that recent research has explored: cosmic flows. Galaxies don't just move. Apart due to cosmic expansion, they also experience bulk motion toward regions of especially high density. These flows are measurable and well documented. What if the Boötes Void and other supervoids represent source regions for particularly strong flows, where matter has been efficiently drained away by the gravitational pull of some distant, massive structure? Observations support this to some degree. The Shapley supercluster, one of the most massive known structures in the nearby universe, sits relatively close to several major voids. Its immense gravitational field creates a flow pattern called the Great Attractor, pulling matter from surrounding regions. Perhaps the voids are simply shadows, zones depleted by this cosmic drainage system. Yet this explanation too has limits. The timescales still don't quite work. The speeds involved don't fully account for the degree of evacuation. Something remains unexplained. And then there's the question nobody likes to ask, but everyone thinks about. What if there's structure within the voids that we simply cannot detect? Our observations depend entirely on electromagnetic radiation, light, radio waves, X-rays. If some form of matter or energy doesn't interact electromagnetically, we're completely blind to it. Dark matter already proves this point. We only infer its existence through gravitational effects. What if the voids contain something even more elusive? Structures composed of particles that interact only through gravity, or perhaps through forces we haven't discovered yet. This ventures into speculation, but it's grounded in honest humility. We know we're missing most of the universe's content. Roughly 95% consists of dark matter and darker energy, substances we cannot directly observe. Is it really so unreasonable to wonder if vast regions of apparent emptiness might contain invisible architectures? Some researchers have proposed looking for gravitational lensing effects within voids. If massive structures exist there, they should bend light from background galaxies in detectable ways. So far, searches have found nothing definitive. But absence of evidence isn't evidence of absence, especially when searching for something you don't know how to characterize. The philosophical implications of supervoids extend beyond astrophysics. They touch on questions about cosmic variance and observational selection effects. We observe the universe from one particular location at one particular epoch. What if our cosmic neighborhood isn't representative? What if the rules governing structure, formation vary subtly across the observable universe in ways we haven't accounted for? This possibility that our local patch of cosmos might not reflect universal laws is both thrilling and terrifying. It would mean our cosmological models, painstakingly built from local observations, might not apply everywhere. Like ancient civilizations believing their land was the entire world, we might be projecting our local experience onto the whole. But evidence for true cosmic variance remains elusive. The cosmic microwave background shows remarkable uniformity across the sky, suggesting the universe's fundamental properties are consistent everywhere we can observe. Yet supervoids still sit uncomfortably at the edge of what our models can explain. In 2013, a team led by Istvan Sapudi announced another disturbing finding. They discovered a correlation between the cosmic microwave background's cold spot and a supervoid at redshift 0 and 15 in about 1.8 billion light-years away. The void's gravitational deficit appeared to be affecting the ancient light passing through it, creating a temperature depression. But the magnitude of the effect was wrong. Too strong. The integrated Sachs-Wolf effect, which governs this interaction, couldn't fully account for the observation. Some physicists suggested systematic errors. Others proposed exotic modifications to general relativity. A few even revived old ideas about cosmic strings or other topological defects from the universe's earliest moments. None of these explanations gained widespread acceptance. The mystery deepened. And here's what haunts researchers late at night. If we can't explain structures as basic as voids, regions, defined by the absence of matter, what does that say about our understanding of the universe's architecture? If the empty spaces don't make sense, how confident can we be about the filled ones? Today, surveys like the Sloan Digital Sky Survey and its successors continue, mapping cosmic structure in unprecedented detail. Each new dataset refines our understanding of void statistics, their size distribution, their evolution over time, their relationship to surrounding structures. The Boötes Void remains the most studied, but it's no longer the most puzzling. Larger, stranger voids continue to emerge from the data. Some researchers now focus on void edges, the boundaries between emptiness and the cosmic. Webb's filaments. These transition zones show complex dynamics. Galaxy clusters form preferentially at void edges, where matter evacuating the void's interior meets the Webb's filaments. Understanding these boundaries might unlock the void's formation mechanisms. Others investigate whether voids affect local physics. Could gravitational waves propagate differently through underdense regions? Might fundamental constants vary ever so slightly? These are long-shot ideas, but in the absence of conventional explanations, creative thinking becomes necessary. The truth is, we're still at the beginning of understanding cosmic voids. The Boötes Void was discovered only 4 decades ago, a blink of an eye in astronomical terms. Major surveys covering sufficient cosmic volume to properly characterize supervoid populations only became possible in the past 20 years. What we know for certain is this: the universe contains enormous regions where almost nothing exists, and these regions are larger than standard cosmology comfortably predicts. We know they're real, not observational artifacts. We know they're growing as the universe expands, and we know our best models strain to explain them. What we don't know is whether they represent an extreme, but natural outcome of cosmic structure formation, or whether they're pointing us toward new physics. We don't know if they formed passively through gradual matter evacuation, or if some more violent process shaped them. We don't know if they contain hidden structures invisible to our instruments. The Boötes Void sits there in the constellation of Boötes, the herdsman, unchanging on human timescales but evolving on cosmic ones. It contains perhaps 60 galaxies in a volume that should hold 2,000. It spans 330 million light-years of near emptiness, and every time we look at it with more sophisticated instruments, hoping for clarity, we find new questions instead of final answers. Perhaps that's the void's most unsettling feature. Not its size, not its emptiness, but its persistence as a reminder that even the empty spaces in our universe remain fundamentally mysterious. We've mapped its boundaries, catalogued its few inhabitants, measured its expansion. Yet we still can't fully explain why it exists. And in a universe that's supposed to follow knowable laws, predictable patterns, mathematical certainties, that silence, that absence of answers, echoes far louder than we'd like to admit.